are going to do a couple things. We're going to, if you want to do the precipitation lab, that's going to be open. It takes about 5 minutes to do. We'll do that after the finished lecture. We are going to, it's not moving for me. Now it's moving a lot, thank you. We're going to finish stoichiometry up today and do percent yield. We're going to do the teddy bear stoch lab, which is just a real quick little lab. But then you also picked up as you came in the pre-lab and lab for 5.1, which is one of the labs that we have to do. So the green is the procedure. The white that's stapled together is your part that you're going to be handing in to me. You will, for part of the pre-lab, have to grab the books to get that done, but we'll start that after. Okay, so we're going to go into your chemical reactions. We are down here at the bottom, about right here, and we're going to start from here. Okay. No, it's not points. Okay, it's just for practice so that you're good for the test. Okay? The teddy bear one is not. The one that came out today, yes. There's 2 pages to it. So that one is no. But that one is good practice for the test because you'll be doing that on the test. So you want to make sure you do that. You got your ears lowered. That's what I meant. Okay, so remember when you're doing stoichiometry, you need to have an equation and it needs to be balanced. If it's not balanced, then you have problems. So we have a balanced equation up here. I like to put what they give me underneath it, because if I put what they give me underneath it, I can easily compare them and find out what is the smallest. Okay, so as I'm looking here, it's a 2 to 6 ratio. Well, both of those can be divided by 2, right? So it's basically a 1 to 3 ratio. I just want to have 3, need to have 3 times as much of the hydrogen bromide or hydrobromic acid as I do have of the aluminum. And if I look at that, aluminum I have about a little over 3. Well, 3 times that is 9. Do I have 9 hydrobromic acid? I don't. So because I don't, then I know, oh, hydrobromic acid is my limiting reactant. So I'm going to take that down and put it here. And because it's my limiting reactant, that's the one I'm going to use to figure everything out. So I take it and I start here with 4.96 moles of HBr. Now, next thing I do is find out what I'm trying to find. And that is question mark moles of H2. The ones that we're going to do right now for stoichiometry, we're just going to go moles to moles. But know that they could give it to you in grams, and you have to change it into moles before you do what we're doing today. Okay? Okay, so if you look at the coefficients, it's 2 and 6, right? I can reduce both of those by 2, so it would be a 1 to 3 ratio. So for every 1, I need 3. And I look at aluminum and say, okay, I have 3 aluminums, and I need 3 times that much hydrogen, or HBr. Well, 3 times 3 is 9. I don't have 9. I only have 4. So that one I'm going to run out of first, is the HBr. Okay? So now what I'm going to do is I'm going to look at, I wrote over that, sorry. I'm going to look at this coefficient and this coefficient, because now that I'm in moles, I can use the balanced equation to go from moles of one thing to moles of another. So I put the 6 moles of HBr on the bottom, and I put 3 moles of H2 on the top. Moles of HBr go out. Okay, I take and times this through, divide by 6, and I'm going to get moles of H2, which they wanted. We have 3 significant figures. We should have 3 in the end. We're basically dividing it by 2, right? So what do we get? 2 point something. 45, 48, 2.48. That's me doing it in my head. You'll need calculators out. If you don't have them out, grab them out. Or borrow mine. So I did do it right. Okay, so now the next part here, I'm going to actually write up here, but for the reactant in excess, so that one is my aluminum. I know my aluminum is going to be my excess. How many moles are left over? So first of all, I need to know how many moles were used, right? So I'm going to again start with my limiting, which is the 4.96 moles of HBr. And this time, I'm going to convert it between these two. I'm going to try and go back to aluminum. So I'm going to take that 6 moles of HBr and 2 moles of aluminum. HBr goes out. So this time I'm basically dividing it by 3. So I'm going to end up with 1 point something moles of aluminum used. So somebody do that calculation for me real quick. If I'm in moles, I can take the coefficient and go from moles of one thing to moles of something new.
Yeah, so you take the moles of HBr and both those.
I always use my limiting. That one's going to tell me what I used.
And then on the bottom, you use the opposites.
So I'm in HBr. I want to get out of HBr. That's when I use the coefficient on the bottom. Okay, so what do we get? 1.65. We're just going to take 2. Now, from up here, I'm going to take this and put it right here, 3.22. That's what moles of aluminum that I started with. Okay, I'm going to just subtract those. And what's left over is what didn't get used, right? So again, I'm going to end up with 1 point something moles of aluminum in excess, meaning I didn't use it. How much did I not use? 1.57, almost enough to do a whole nother round, right? Okay, so that's what wasn't used. So if I'm over a company that is trying to make this aluminum bromide and hydrogen gas, I'm going to say, hey, we're using way too much aluminum. Aluminum's expensive, and we're wasting almost enough to do another round. So we either need to get more hydrogen bromide or hydrobromic acid, or we need to reduce the amount of aluminum we're using. Okay? All right, so let's do another one. Okay, this one gets a little bit more tricky because it's not as easy to see. So this one is 21.44, and this one is 17.67, or 62, sorry. And it's a 3-to-2 ratio. That's harder, right? I don't really know. I know that the silicon is more, and it should be more, but I don't know if it's the right ratio. So it doesn't matter which one you use. Take one of them. I'm going to take the first one, 21.44 moles, of silicon, and I'm just going to quickly change it into moles of nitrogen. So I'm going to put the 3 moles of silicon on the bottom, 2 moles of nitrogen on the top, and I'm going to figure out what it is. How much nitrogen would be needed to go with that 21.44. And see if it's bigger or smaller. 14 point what? One more. 29. Okay. So 14.29 moles of nitrogen is needed. Well, I've got more than that, right? So that means silicon is my limiting reagent. Now, if you happen to end up with less than that, then you would know that the other one is. Okay? Again, start with what my limiting is, which is silicon, 21.44 moles of silicon. Now I look at what they want. They want how many moles of this. So I look at the coefficients. It's a 3-to-1 ratio, so 3 moles of silicon for every 1 mole of trisilicon tetranitride. And I cross out silicon. And I should end up with 7 point something. 7.114. Awesome. Okay, moles of silicon trisilicon tetranitride. Okay, now we could easily change that using the mole map into grams if they wanted to know the mass, right? We just have to do another step. So let's look at the bottom one. In excess, we have nitrogen, right? So we're going to go through the same steps that we did before, but we already found the number of nitrogen that we're going to use. So we don't have to redo what we already did. Now, if I picked nitrogen and gone to silicon, I'd still have to do that. But I picked the right one, so that's good. So on this one, we're going to take 17.62, which is what we started with, moles of nitrogen. That's what we started. And then we used up 14 point, what was that, a 29 moles of nitrogen used. We're going to subtract that. We get 333 moles into in excess. Okay? So when you have to change up top, when it's really too close to really figure it out, you do have to do a calculation, but in the end it saves you some time. Sometimes, if you pick the right one. Okay? All right, so let's go and have you do the next one all by yourself. I want you to try it all by yourself. I'm going to give you some time to get head started on it, and then I'll put it up and let you see. If you're really, really lost, pull me in right now. This is the time to get some extra help. Okay. because I know a lot of you had questions. Okay, so first thing, put underneath what you had for each thing. It really does help if you do, okay? It really makes you look at it with the numbers right there. And then if you can reduce these right here to get an easy ratio, do it. Since it's a 2 and a 4, they both divide by 2, so I have a 1 to 2 ratio. So for every 1 copper chloride, I need twice as much potassium iodide. Well, this is a real easy one. 0.5 times 2 is 1. I don't have 1. Because I don't have 1, my limiting reagent is Ki. Okay? Then I use this for everything. Okay? So I start 0.64 moles of Ki. Start with my little T-chart. I'm going to use this going to here because it wants to know how many moles of I. So 4 moles Ki on the bottom, 1 mole of I2 on the top. Moles of Ki go out. Then you should end up with 0.16, I believe, moles of I2, right? Okay, now down here, we're working about the excess. We want to know how much is left over. Well, first of all, we need to know how much we used. This is my copper chloride, and I always do this so I know which one I'm looking at. But I still start with the potassium iodide. So I start with my potassium iodide. But this time, I'm using this ratio. Okay, so I'm putting 4 moles of Ki on the bottom and 2 moles of copper chloride on the top. And my moles cancel out. I go ahead and don't reduce that. Just do it as it is because that's where I find most kids make their mistake because they try and reduce it and then plug it through. Your calculator doesn't mind doing the extra work. Okay, so 0.64 times 2 divided by 4, and we get what? 0.32 moles of CuCl2 used. Used. This is where a lot of kids stop. Don't stop there. That's how much I use. That's not how much is left over. I have to take this and take 0.56 minus that to get how much is still left over. Okay, so we get 42.0 mole of CuCl2 excess, meaning leftover. That's how many buns or tomatoes or whatever I have left over. Okay? We okay? Understand? Do we have any part that we need to go back over? Really important. Yes? Okay, limiting reactant. I just am going... This part? The excess? Okay, so once I found out my limiting reactant, I'm still going to use it every time I do a calculation. To find out how much in excess, I'm taking my limiting reactant and I'm going back and finding out how much of my excess reactant I used. Because I'm going to have to put so many hamburgers and hamburger buns together to make a hamburger, right? I want to know how much I'm going to have left over. Okay? So when I do that, that's where I'm using these coefficients right here to get this number, 0.32. Okay? Once I've got the 0.32, that's how much I used. This number right here was what I started with. I started with that. So I've used that much. I just subtract them and I find out how much I had left over. Does this make sense? I lose you again, Luke. Okay, everybody else got it? Any questions? Please feel brave enough to ask.
We're doing homework, right?
I think so. Yep, one more. Okay, this is on your own again. See if you can do it all by yourself. If you need help, pull me in.
11. Holy crap.
But put your numbers underneath them first and just sort of think it out. You don't necessarily have to do any math at first to figure out what the limiting is. Which one do you need more of? Which one don't you have more of? Mm-hmm.
So right here, you need
4 FES twos.
To 11, right.
So multiply that by 4, multiply that by 11.
Well, no, look at it. This is 4. You need, for every 4 of these, you need 11 of these.
Mhm.
This is 26,
Yeah.
right? If I times 26 by 4, I'm going to get a really big number, right? I only have 5.
Yeah, makes sense.
Which one's going to run out?
That one.
Right. So you don't have to necessarily do the math. You can just look at it and say,
That would be like,
which one am I going to make? Yeah, which one?
close to 60, and that's like 120.
Right. So this one right here
It's gonna be
is going to be my limiting because I need 11 of them compared to 4, but I have 26 versus 5, right?
Oh, 26.
26 versus 5, and it's a 4 to 11 ratio, so I need more of this than I have of this, but I have more of that than I have of that. So I can just look at it and say, oh, I know what my limiting is, and move on. Okay? So you got it?
Yes.
Okay, now move on.
So to get that after 3.96, we have to go.
And you got this? Okay.
How many moles of sulfur?
So do you have to simplify it there, or does that start?
So this one we're going to SO2, so 8 on top, and you would have, this is your limiting.
Oh, 11.
This one is your limiting, because for every 4 of these, I need 11 of these. But I have 26 of this, and I only have 5 of this, and I need more of the oxygen than I do the Fe, right?
Oh, yeah.
So the oxygen's my limiting. It's fair, this one. See how we did. Should have given you enough time to run it through. So again, I like to put it right underneath because then I can see really quickly 5.44. I need more oxygen than I have iron sulfide, but I have more iron sulfide than I have oxygen. So right there I can say, oh, O2 is my limiting. That means I'm going to use that in all calculations. So coming up here, 5.44 moles of O2. Last conversion, I'm trying to find moles of SO2. So I put 11 moles of oxygen on the bottom, 8 moles of SO2 on the top. Moles go out. Again, they could ask you for how many grams are produced. If they do, then you'll have to add up the mass of sulfur dioxide and put it on the top, 1 mole on the bottom. Use your mole map. Okay, what do we get here? 3.96. Do I have a second? All right, awesome. Okay, then down here, the excess is the iron 4 sulfide. This right here, we're trying to find out how much is left over. So we're still going to start with our limiting. 5.44 moles of O2. We're still going to put the 11 O2 on the bottom. 11 moles of O2. But this time we're going back to FeS2. So we're going to put the 4 moles of FeS2 on the top. When you run this through, what do we get for this moles right here? 1.98. Okay, that was the moles used. Moles of FeS2 used. I don't want to stop there. I can't tell you enough how many kids stop there. That will be one of the multiple choice answers. Don't let it throw you. You have to come back and say, oh, this is how much I had. I used this much. How much is left? 24.94. And my boss is going to be ticked at me for using all of this in excess that gets wasted, because that is money out of his pocket.
You don't have to waste it, you can use it again.
You can sometimes. Sometimes you can recapture. Sometimes you can't.
Yeah, that would be upsetting because you're wasting more than you're using.
Right. So when we do stoichiometry in industry, we need to make sure that those numbers are really close to each other so that we don't waste much. Now there's some that we want to make sure we have excess oxygen so we get to the oxidation state that we want, but this isn't one of those states. Okay, so last thing that we got to learn for this test is reaction yields. This is the easiest part. Okay, you guys have all, from when you're little, figured out what your percentage on the test is, right? That's what you're doing. Okay, it's actual divided by theoretical times by 100. Theoretical is just what's the maximum I could have got. Okay, so here is what I got in lab. This is what I figured out I should have got in lab. What's my percent? Times by 100, and that'll give me my percent. We usually report percent to 2 after the decimal, so go ahead and give me a percentage. How much?
73%.
73%. 73 point what? 98? 96. 72.96. Okay, in industry, we like to have 80% or better yield. If we don't have an 80% or better yield, I lose pay steps. To the point, if I'm really bad, I lose my job. If I'm above 80% and above 90%, 90 to 100%, I'm up for a promotion to keep my job and do better. If I have above 100%, what do you think? I'm fired. Because I don't know how to do math, because you can't get over 100% yield. You're doing something stupid. Okay, so let's go on to this one. Would you find the percent yield for the top one? We're going to do the bottom one together because it's a little bit more tricky. So quickly find the percent yield for the top one. And is this person going to get fired or promoted? Fired or promoted? Okay, find your percent yield, fired or promoted for the top one. I heard fired, I heard a promotion.
I heard 95.
95.36%, they're getting a promotion. Okay, now, next one. This one is where we put everything we've got and put it together and do it all in one problem. So let's read it through. The reaction started with 384 grams of S6. Assume that unlimited supply of oxygen. So the S6 is my limiting. What is the theoretical predicted yield and the percent yield if only 680 grams of sulfur dioxide are produced? Okay, that's a lot of stuff. What is the first thing I need? No. First thing I need. We're putting everything together that we've just done. I need a reaction, and I need it balanced. So S6 as a solid is going to be put with oxygen. How do I write oxygen? O2, and oxygen is a gas, right? I'm going to get what as a byproduct? Sulfur dioxide, which is SO2, and it is a gas also. So what is the next thing I need to do? Balance it. What do I need to do to balance it? Okay. At this point, I like to put that 384 underneath here, so I know what I have. I also like to put a question mark here and grams, so I know what I'm going to. Okay?
So you have to change the sulfur water.
Right. Now, since I have to go, I can't change it mole to mole unless it's in moles. So I'm going to have to change those grams into moles. So in order to do that, I'm going to have to add up that sulfur dioxide. So sulfur is 32.06. Oxygen, I have two of them at 15.999. What's that total? More than that. Plus the sulfur. How much? That's how many grams are in 1 mole of sulfur dioxide, right?
So can we put that under the SO2?
So nope, I'm just putting it off to the side. Now I'm going to do the stoke, because I've got to go from here to see how much I could have made. So when I do stoichiometry like this, that tells me my theoretical or what the test total was. Okay, so we're going to start with 384 grams of S6. First thing I need to do is convert that to moles. So I'm going from grams to the center mole, which is yellow there. So I'm going to have 1 mole of S6 on the top. The reason why I did not add this up is I'm just going to go 6 times sulfur's mass on the bottom for the grams of S6. Because I can do that in my calculator. I don't have to redo it. Okay? Grams of S6 go out. Now I'm in moles. At moles, I can come up here and say, okay, there's a 1 here, there's a 6 here. So for every 1 mole of S6, there are how many moles of SO2? 6 moles of SO2. Moles of S6 go out. And the last part would be what? Going from moles back to grams. So in 1 mole of SO2, there's 64.058 grams of SO2. So we're going to get that number. Remember, when you have something like this that's big, when you go to divide, go parenthesis, and then close your parenthesis when you're done. That parenthesis didn't want to close at the end. There we go. So give me a number. We started with 3 significant figures. We should end with 3 significant figures here. And just as a thing that you should know, since they gave us how much we got in lab, is this number going to be bigger or smaller than this number? Is the number we're calculating going to be bigger or smaller than this number?
Can you explain?
Should be bigger. Okay, because this is my test score.
Oh, yeah.
So the test is probably out of more, right?
Can you explain each one, how you got each of those numbers?
Okay, so 384 was what was given. Then I had to change it from grams to moles, so I did 6 times the mass of sulfur because it was S6 in 1 mole. Then I used this ratio right here to get out of S6 and go to SO2, so 1 to 6. And then the last part was to go from 1 mole to grams. Okay? Okay, what do we get? I think it's 700 and something. Do it again, calculate it. It should be 700 and something. Yep, 767. Okay, so that's the total for the test. And I got a score of 680. What's my percent? That's it. That's all you're doing. That's a score on the test. That's what I got. So 680. Sorry, this does not write over here in the corner. 760. Yeah, it's not writing. I'll do it over here. 680 times it by 100 equals what? I get to keep my job. Not in promotion yet. 890 and above.
I mean, if you got to find out an answer, you can take the job. Find that answer is the hard part.
Okay, so what was the hard part about it? It's still stoichiometry. It's still what we've been doing. Grams to moles, moles to moles, moles to grams. So it really sounds really weird, but this was sort of pounded in my head. Grams to moles, moles to moles, moles to grams. Grams to moles, moles to moles, moles to grams. Grams 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 to moles. Okay, you always got to be in moles when you're in the equation. When you're using the equation, you have to be in moles. So whether you're in molecules or whether you're in grams, it has to move to moles before you can use the equation to go from one thing to a new thing. Okay? All right. How are we feeling about this? We need practice. Okay. Guess what? That's it. That's all that's on the test. So at this point, what we're going to do, and we've got about 40-ish minutes, a little less than 40-ish minutes, we're going to do the teddy bear really quick, and then if you want to go back and do the lab for 5 minutes, you can. And then the rest of the time is for you to work on Learn Smarts, to work on homework, to work on your pre-lab. So if you will grab your teddy bear thing for me really quickly. I like this, by the way. On second thought, maybe you should go outside to kiss the bride. Cola and Mentos. Dude, I think you seriously are overreacting. Okay? Not that one. Not that one. Where is it? Right here. This one. Okay, so basically we're just going to go really quickly and talk this through. And we sort of done this from the last one. I didn't erase it. So basically a chemical equation is a ratio. It is a recipe on how to put things together. So if I were to make s'mores for 35 students, I would need to have 70 Teddy Grams. I would need to have 105 chocolate chips. I would need to have 35 marshmallows. That would give me 35 Teddy Bear s'mores, right? So we're just using the ratio. Now, if I go down a little bit more, if I have 20 Teddy Grams, so I have 20, so I can make 10, right? Because it's a 2-to-1 ratio, using the ratios. Okay, how many marshmallows would I need? Well, if I have, it would have to be 10, and then chocolate pieces, I take that 10 and times it by 3, which would be 30. And you can go down and do the rest of this and just sort of think through it. I'm not going to make you do it. The lab part, sometimes we actually weigh out each of them and have them show it, that the weight does stay the same on side to side. So I'm not going to really stress that on you, but we're going to go to the procedure here. So on the procedure, what you're going to do is you're going to come up and get a cup of stuff, okay? And you're going to dump it out. I've got some paper towels over there. You can dump it out if you want to. And you just count how many you have of each. And you figure out how many Teddy Grams you can make. Now, I do have little Bunsen burners that you can roast your marshmallows over with toothpicks. And you can actually make your little s'mores. Okay? It's up to you if you want to take the time to do it. You can figure out your percent yield. You can figure out your theoretical yield. For your theoretical yield, that's what I give you. You should be able to make 4. Okay? If you're able to make more, we've got problems, but say 4. Huh? If it broke in half, you can't use it.
No, we.
What if everything magically happens to split in half?
Nope, doesn't work that way. Okay, so time is yours. You can work with how you need. If you need help, I'm here. The stuff is up here, so come help yourself.